All right, so in physical oceanography and in fluid dynamics in general, the pressure force is a very important force for the motion of fluids for continuums. And so I want to tell you a little bit what is the pressure force. I've already introduced it before when we did the hydrostatic balance, but I want to review it again because of its importance. So let's imagine a little volume of fluid, and I'll fix it like a little box like this. And this coordinate, I'm going to do it in Cartesian coordinates to make things as easy as possible. So this corner of the box here, I'm going to give it x, y, z coordinates. And then the width of the box, this will be of width delta x in this direction, delta z in this direction, and then delta y in this direction. All right, and now we're going to try to calculate what's the net force on this little box of fluid given by the pressure. And so pressure, as you know, right, is has dimensions of force per unit area, right? So it's the force per unit area, and the pressure is not a force itself because it's a scalar quantity, right? It's just the pressure doesn't have a direction, but forces need a direction and a magnitude. Pressure only has a magnitude. So how do we go from a pressure to a pressure force? That's the issue. And so what we can calculate on this little box here is the net force from the pressure acting on all the different faces of the box. And so let's start in the x direction. X direction. So there's going to be a force pushing on the box, right, from the left on the face of dimension dz dy, right? So that face on this side has height dz and depth into the board dy, and the pressure at that on that side is p of x, y, and z. So then the force acting on this side is going to be p of x, y, and z. That's the force per unit area times the area, which has dimension delta z times delta y. Right? And then there's also going to be, so that's pushing in the positive x direction, right? X is increasing in this direction, and y is increasing in that direction, and then z is increasing upwards. Okay, and there's also going to be a force in the x direction acting on the face on the right-hand side, but this time the force is acting from the right, so it's pointing in the negative x direction. So we have to subtract minus p, and now on this side we're no longer at x, we're moved over, right, by delta x. So it'll be x plus delta x, y, and z times the area, and since I have a nice little box, this is also area delta z delta y. All right, so that's the net force in the x direction on the box. Now, if we now divide out by the volume of the box, right? So in fluid mechanics, we always, since we're going to deal with the continuum, we deal with forces per unit volume. And so I'm going to divide out by the volume of the box. So the volume, delta V, is just delta x times delta y times delta z, right? It's just the height times the width and the depth. So if I divide through, so force per over delta V is going to be equal to p of x, y, and z minus p of x plus delta x, y, and z. So when I divide through by delta v, the z and the delta z delta y will cancel from here and from here, but I'll be left with the delta x, right? Nothing cancels out, so I'll have it on the bottom, delta x. And now, if you look at this, it looks a lot like the derivative, right? The only thing is when we do the derivative, we take the limit as delta x goes to 0, and it's the other way around. We say p at x plus delta x minus p at x, right? So this is just the negative, so that's equal to minus. And I'll do it for this one. X plus delta x, y, and z minus p at x, y, and z divided by delta z. Delta x divided by delta x. Right? And if I take the limit, so the limit as delta x goes to 0 of the force, and this is in the x hat direction, fractions of the force per unit volume is equal to, or I could do as delta x goes to 0, or as the delta v goes to 0, it wouldn't really matter. So by delta v would work also, because anyways these things cancel. But the upshot is it becomes the minus the partial derivative of the pressure with respect to x. And the same reasoning will work also in the y direction, right? It'll be the same thing will follow through. This time when I divide out by the volume, what will cancel out is the delta z and the delta y. And I'll be left with 1 over, the delta z and the delta x will cancel out, and I'll be left with 1 over delta y. So if I take the force in the y direction, I'll get minus dp dy. So let me write out in general. So this one in the x direction, same thing will happen again. I'll get just minus dp dy, and same thing in the z direction. Minus dp dz. And these are exactly the 3 Cartesian components for the gradient of the pressure. So the force then, the force for the pressure, right, is a vector, and it's equal to minus the gradient of the pressure. And that should be a little bit intuitive. The force will act from a region of high pressure to low pressure. So if you compress something, it wants to flow, it'll accelerate things away from the high pressure towards the low pressure. So a garden hose works that way. You turn off the faucet, there's pressure upstream, and that force causes the fluid to accelerate down the hose and spray out the other end, right? So that should be intuitive enough. So in fluid dynamics, we very often need to worry about the forces, and what we do is we use the pressure force, which is, remember, a force per unit volume, and we can check the dimensions of that, and we should do that. So let's check that it has the right dimensions. So the dimensions of the pressure force, right, is going to be equal to the dimensions of the minus the gradient of the pressure. And so we'll have the gradient has the units of inverse length, right? So this will be 1 over length from the gradient, right? Because it's like d by dx or d by dy or d by dz. And all those have units of inverse length. And the pressure has units of force, which is mass times acceleration, right? And an acceleration is a length per unit time squared. So this is the force per unit area. So I have to do a length squared, right? So these are the dimensions of the pressure, right? Force, which is mass times acceleration, mass times length over time squared, per unit area, because it's the pressure over length squared. And this gives me, these two together, I get 1 over L cubed times mass length over time squared. And this has dimensions of force, and this has dimensions of volume, or inverse volume, And so we see that indeed the pressure force has dimensions of force per unit volume.